Alrighty, folks. So this is for our problem session here on week 6. Don't have quite as many problems as we have been because there were a lot of overlaps in the questions. Hopefully that means we'll get to be super efficient about it. But to start off, we're going to do a problem from the book, section 3.7, number 59. So that one looks like y equals cosine of 1 plus x all over 1 plus cosine x. And the instructions were to find y prime using the appropriate rules. So basically it's saying don't go back to the definition because, for one thing, that sounds just awful. But go ahead and use our rules here. And there's two rules that apply, right? And right off the bat, we see it's a quotient, right? So it's one thing divided by another. So if we look at it, the low is 1 plus cosine x. And that one's pretty easy to take the derivative of. We don't even have to use any rules. Well, I guess we're technically using the constant rule. But the derivative of the 1 goes away, because 1's just a constant. And the derivative of cosine x is negative sine x. All right, so just to be clear about that, the 1 becomes 0. This becomes negative sine x, so we get out of that just negative sine x. The numerator, the high part, is cosine of 1 plus x, and this is where we're going to need to use another rule, and specifically the reason why it's in this section, we need to use the chain rule. So with the chain rule, that means there's an inside and an outside. So the inside here, well, it's what's being plugged into a function. That's the 1 plus x. And the outside is what the inside is being plugged into. So that's cosine of x. So if we take the derivative of the inside, well, again, that 1 becomes a 0. The x becomes a 1. And if we take the derivative of the outside, that, again, we figured that out before. That's negative sine x, right? And we did all this so that we could get d high, right? Because high is the piece that needs the quotient rule. And the way the quotient rule works is that it's the derivative of the outside with the inside plugged in. So it's not negative sine x, it's negative 1 sine of 1 plus x, because we got to plug that inside back in, times the derivative of the inside. All right, so negative sine of 1 plus x, because multiplying by 1 doesn't change anything. Right, so to go back to using the quotient rule on the original guy, quotient rule is low d high minus high d low over the square of low we go. Right, and you could do some simplifying if you really wanted to. Mostly that would involve bringing this negative out here and having them cancel. I guess you could distribute if you wanted, right? So maybe you get negative sine of 1 plus x when you distribute it here. When you distribute it here, it becomes negative cosine x sine of 1 plus x when you multiply these two together. And then when we simplify this, it becomes plus cosine of 1 plus x times sine of x when we multiply that through. And we can't really do anything about the bottom because there are no factors that look like this up top, right? You might be thinking, why didn't I cancel it with that? And that's because you're not allowed, and that's bad algebra, and it's horrible habits that everyone falls into, which is the only reason I'm highlighting it. You can only cancel factors, right? So the fact that this guy doesn't have a factor over here means we can't cancel it in total. This is just part of a term. It's not a factor of the numerator. And you can only cancel factors when they show up on both the top and the bottom, right? So we can't cancel out with this one either because it's part of a term. It's not a factor of the numerator. Right? If this were an exam, leaving it up here would be just fine. By the way, for me. So, next up from the book, from section 3.9, number 65. That one said y was equal to sich times coach, I think is how you pronounce that. I don't really know. It doesn't matter too much. And again, we had the same directions here. Find y prime. So this one, the thing we got to do, notice first off is it's a product. So we're going to use the product rule, right? So y prime is going to be the first times the derivative of the second plus the derivative of the first times the second, right? And then looking at the section that this came from, we have formulas for these two derivatives. This one is negative cosec squared x, and this one is negative sec x tanh x, right? Which mirror fairly well the way the non-hyperbolic trig functions go. They're slightly different, so you will want to have a reference for them. But they have similar patterns, right? And one pattern they have in common is that tanh and cotanh cancel each other out. They're reciprocals of one another. And we also notice that we have this negative sec that we can pull out of the whole thing. Right, that leaves a cosec squared x here. And once tanh and cotanh cancel one another, all we were left with was that negative sec. So this becomes 1. Right. So that's what we got for this guy. Now, I was, I guess, proud to note, but a little bit annoyed at the software, that a lot of the problems that folks asked about were ones that were more complicated than I intended, because the software had some unexpected output in terms of what the problems look like. I will, mention what I expected certain things to be, but then also talk about how you can do these guys. The main deal is that with the way some of them worked, the problems are, at least, let's see, 2, 3, 2 and 3, it looks like, are not very doable without something called the chain rule, which, as we noticed here, was from section 3.7, which was not supposed to be on this homework. So those two problems, and there might have been another one like it, I thought were going to have a restricted set of values they could take on, and they didn't. So I'm sorry about that. But it wasn't a big portion of it, and it won't be too much to catch on. They are the simplest versions of the chain rule. So hopefully we'll get these squared away, and you'll be set for the rest of them. But first off, we're settling in on the homeworks. This is going to be like number 2. So this said find the smallest possible x value. Whoops, not possible, positive. Can't even read my own handwriting. where the function f of x equals x plus 2 sine of 3x has a horizontal tangent line. So what I thought is that where this 3 is, right, apparently that's just a random number. So one of the things you'll get if you regen the problem or if you look at the different homeworks is that 3 will be a different number. I thought it was supposed to be 1 or -1 at any given time, which if it's 1, you don't need the chain rule. If it's -1, you can use properties of sine, specifically that it's an odd function. If I recall, I'm pretty sure cosine's the even one. You can use the fact that it's an odd function to not have to use the chain rule. If there's something that's not a 1 or a -1 there, you have to use the chain rule on this problem. But it's a very nice version of the chain rule, right? Because what we're plugging in here is very simple, right? When the inside function is linear, then as we'll see, right, though, okay, I'm getting a little bit ahead of myself. I got distracted by explaining what went wrong with the program and why this one was a little bit harder than it needed to be, to forget to talk about this guy, right? Because this is actually the key of the problem, key of the word part of the problem. The chain rule is the key to this part of the problem. But this horizontal tangent line, right? So if we just look at horizontal line, that means that the slope is equal to 0, right? The definition or a definition of a horizontal line is a line whose slope is equal to 0. The tangent line comes in. That says that the slope is equal to f prime of x, right? So if we're looking at x values, the slope of the tangent line specifically is then f prime of x. So if we combine these two together, we're looking to solve f prime of x is equal to 0. All right, well, first off, we have to find f prime of x, and that's where the chain rule stuff that I started in comes from. So we can take the derivative of x. That's no problem. It's 1. The constant rule says we pull that 2 out. And if you have a linear function on the inside, right, if that's what you have here, right, we have the quick and dirty version of the chain rule that our book kind of presents as its own thing, but it's really just a simplification of the full chain rule that says take the slope of that guy, bring it on, I needed that 3, thanks, bring it on the outside here, and then just take the derivative of the rest, right? So the derivative of sine is cosine, and leave the inside the same. All right, so this 3 comes from this 3 right here. Right, again, using that bare bones version of the chain rule. So we get 1 plus 6 cosine of 3x. Right. So we want to know when this is equal to 0, right? So we can solve that. We get 6 cosine of 3x equals -1. We get cosine of 3x equals -1 over 6. We take the inverse of both sides, or the inverse of cosine of both sides. Right. The inverse and the function cancel each other out. So x itself is going to equal this arc cosine thing divided by 3, right? And there was some other wording on the homework software, and that's just telling you that it wants an exact value, so do not plug that into your calculator and round. It wants an exact value. And the other thing is telling you that rather than trying to write cosine inverse of cosine of 3x, equals cosine inverse of negative 1/6, right? If you were doing that for the exam, either one of those is fine. Arc cosine is cosine inverse. Whichever one you prefer, absolutely go for it. But as we've talked about before, sometimes the software needs specifically to know what something's going to look like. And in this case, this program or this particular question wants to know that it'll look like arc cosine. Right? So that's what those directions were about, and this would be the final answer that we plug in. Right. 3 was the other one that I was expecting to mostly be algebra practice rather than using the chain rule. Right, so for here, well, let me write down what we want to find. Right. So here, when I looked at the example problems that this was going to generate, I happened to get lucky enough that this number was always 1, 2, or 3. So I figured that it would be some good algebra practice for folks, and then practice using polynomials. You can technically do this problem without the chain rule, no matter what that power is. But I noticed for some folks that ask questions, that power got up to like 8 or 9. And that's just unreasonable. I was not expecting you to have to do that. So it's a lot easier, however, if you use the chain rule. And specifically a specific version that our book names called the generalized power rule. And that says that we can use a rule just like the power rule. So we take this 4 and we bring it down out front. And then we reduce the power there. This stuff all stays the same, right? The base stays the same. But then we also have to multiply by the derivative of the inside, right? So in this case, it's 2. Right, so that's the generalized power rule here. It's really the only efficient way to get this done for the bigger numbers. If it was 1, 2, or 3, that's not a big deal. Bigger than that, it gets a little obnoxious. Right, and then when we want g prime of 1, we just have to plug that in. Right. So the next thing it's asking for is g double prime of s. Now note, once you plug a number in, once you get a value, you cannot take the derivative of that piece again. You cannot take the derivative of something that's not a function, and once you've plugged a value in here, you don't have a function, you have a value. So when we want to take this second derivative, we need to take the derivative of this guy. Right, so again, we're going to use that generalized power rule. We're going to bring the 3 out front. And we're going to change the power on this guy to 2. Then we're going to multiply again by the derivative of this piece. And so this becomes 48. That's 2s minus 3 squared. And then g double prime of 1. We get 48 times negative 1 squared. So positive 48. Okay, so that should be all of them that have a problem with chain rule. Number 4 can be done with the chain rule, but it doesn't have to be, and it actually, that's true no matter what values it plugs in. So this is one that the chain rule can be used for, but doesn't have to be. So we have an f of x that looks like this guy. And we want to find the 8th derivative of f at negative 2. All right? So the trick here is that, well, there's a couple things that are a trick here. One, I don't really want to take the derivative 8 times. I don't know about you. Maybe you really like taking the derivatives. Maybe it's fun for you, and you can go ahead and you can take the derivative 8 times. But what I'm going to be aiming to do is find a pattern for my derivatives so that I don't have to do it over and over and over and over and over again 8 times. The other thing is we don't know how to take the derivative of this, right? So it requires us to be clever. And the thing to be clever is we realize that we know the derivative of this guy is that, right? So as long as we have the derivative of something to the x, just plain x, we can take the derivative of it. So that means I'm going to rewrite this to be e to the negative 1/4, then to the x, right? That's how exponents rules. Those are some of our that's how exponents work. Those are some of our basic algebraic rules, if I can get my words correctly. So this is something that we can take the derivative of before we learn about the chain rule. We can take the derivative of this with the chain rule. But the way I intended this to go, right? So we take the first derivative, and that's negative 2 ln of e to the negative 1/4 times e to the negative 1/4 to the x, right? That's using this rule here. And if we simplify this, that's negative 2 times negative 1/4 times e to the negative 1/4 to the x. And what I'm going to do here, I could simplify that, right? We can multiply through. We'd get positive 1/2 out of it. Be all great and dandy, super simplified. But my goal here is to try and find a pattern so that I don't have to do a whole bunch of busy work, because that's not my favorite thing. Right, so this is n equals 1. So I take the second derivative. Got to at least have 2 pieces to find a pattern. Right, so this is going to be all those constants over again. Right, using the constant multiple rule. Then using this rule here, this becomes ln of negative 1/4 times e to the negative 1/4 x. So this becomes negative 2 times negative 1/4 squared e to the negative 1/4 x. And this is for n equals 2. So I'm beginning to see a pattern, right? This is technically n equals 0. All 3 of these have a negative 2 out front, right? So that seems to be fairly stable. And each of these derivatives, I notice I'm going to pick up another 1/4, right? It's not just a coincidence that this is 1/4 and this is 1/4 squared. If I took the derivative again, I would take, whoops, there we go. I would take ln of e to the negative 1/4 again, and I would get another negative 1/4. So this is going to be negative 1/4 to the n for the nth derivative, right? And then we always have this e to the negative 1/4 to the x, right? So if I want to find the 8th derivative, this is going to be negative 2 times negative 1/4 to the 8th times e to the negative 1/4 to the x. And if I want to find this at 2, negative 2 rather, this is going to be negative 2, negative 1/4 to the 8th, e to the negative 1/4 to the negative 2. So if I were to simplify this, I would say negative 2 over 4 to the 8 times e, or times the square root of e. Right? That's about as simple as we could make it. We could maybe cancel out that 2 with one of the 4's, but it'd really only make it look more complicated looking. We can't do anything with that square root of e. That's as exact as we can make it. So we can work smarter, not harder, and not have to do something 8 times. We also could have kept doing this. It's not like this was a big stretch. It wasn't a whole lot of work. We could have done that 8 times and gotten there, right? But I prefer finding a pattern and not doing all that scratch work. Right. So next up, we jump to one like number 9. So that one we had f of x, or we had something that looked like f of x equals a polynomial times a trig function. And it wanted us to find f prime of x. So this is a product rule, right? So f prime of x is going to be the first times the derivative of the second plus the derivative of the first times the second. So the derivative of the second, this guy here, is cosine of x. This one here is just going to be a polynomial. We're going to use the power rule a lot. So we get 4x minus 3. So by a lot, I mean twice. And then times sine of x. Alrighty. So, lastly, we have a question to do one like number 11. So this one says, okay, good. I realized I hadn't checked in a while. Got a little bit paranoid. So a particle moves along a straight line with a position given by s of t equals t cubed minus 18t squared plus 105t plus 11. So this problem asks for a whole bunch of things. So one was find the velocity at time t equals 0. The other one claimed that the particle stopped moving twice at t equals what and t equals what. And it asks for the position at time t equals 12. And it asks for the total distance traveled between 0 and 12. And I think that's probably the one that got most of us tripped up, because we got to be real careful about that, and hopefully the pictures I draw will make it make sense. Right? So first off, it's asking about the velocity and when it stops moving and distance traveled. So we're going to need the velocity, right? So the velocity of the particle is going to be the derivative of the position always. That's just a polynomial here. So we can use the power rule a bunch. And this time a bunch means 3 times. Right? So looking at this guy, let me get some colors in here. Right? This is going to be v of t, and it's going to equal 105, or sorry, not v of t. It's going to be v of 0, right? That's what this statement means. And that's going to be 105. V of 0 is pretty easy to find, or 0 of any function is pretty easy to find for a polynomial, right? So stopped moving, right, here means that the velocity is 0, right? Because whenever you're not moving, the velocity is 0. So if we want to solve when this polynomial is equal to 0, we probably need to factor it. So first off, I notice that I can pull out a 3. And then I notice that I can think of 2 numbers that multiply to get 35 and add to get 12. And that is minus 5 and minus 7. right? So, if we solve this, whoops, I got a little excited. So, man, clearly tired. V of t equals 0. So it's going to stop moving at 5 and 7, right, when we solve that polynomial thing. All right, position at time t is also not too bad. That just means taking, well, I guess, s of 12, right, and I went ahead and plugged that in, did all that adding ahead of time. That's just going to be 407. That's just what you get when you plug 12 into s of t. All right, so the tricky one, the total distance traveled between. So, if we think about our velocity function here, right, well, we know it's going to hit 0 at 5 and at 7. Right, and we know that its velocity over here at 0 is somewhere positive. Right, furthermore, we know it's a polynomial. Right, if we dredge our minds way back to the shrouded past of when we took pre-calculus, right, we probably remember that we can only cross the line at zeros. So we're probably going to there. And that because this 0 has an odd power, we're going to break down through it. We're not going to come up again until 7 because we can't do anything with the x-axis until another 0. This also has an odd power, so we go back through it again. Right? And the point of that is that velocity is going to be positive here, negative here, and positive here. Right? So, if we look at the line that our particle is traveling on, right, it's going to be traveling forward until t equals 5. Then it's going to start moving backwards until t equals 7. And then it's going to start moving forwards again until we get to t equals 12. Right? So when this particle moves, velocity of being positive means that it's moving forwards. Velocity being negative means that it's moving back. And then since the velocity goes positive again, it starts moving forward again. So what we really need to do to get the total distance traveled, right, is we need to figure out how long was it going forward, right? How long was it going backwards? And how long was it going forwards again, right? So what we really want to do is we want to take this line and we want to straighten it out before we measure it. Right? Because that's going to be longer than if we just measured from here to here. Right? This would be, the length of this would be the position, just not with P, silly Danny. The position at time 12 minus the position at time 0. Right? I know that that's what a few folks did when they were working on the homeworks. So that's just going to tell you the displacement. That's going to tell you how far it was from where it started. But if we take this line and stretch it out to be straight, it's actually going to be longer because we're going to get this guy sort of swinging out there and pushing everything forward. So what we really need to do is this distance is going to be s of 5 minus s of 0. Right? Let's see. Let's go to colors again for help here. Go away. Okay. This distance is going to be s of 5 minus s of 7. And this distance is going to be s of 12 minus s of 7. And we're going to want to add all those up. So again, I just sort of plug stuff into there. I'm not going to do the algebra in front of you, because I presume we can plug stuff in and be okay. So let's actually give myself a little bit more space here. So this is 200, this is 4, this is 200 again. So the total distance traveled is 404, right? Because we went 200 forward, then we took 4 steps back, and then we took another 200 steps forward. So our Fitbit tells us that we walked 400 steps, right? The mile marker that we passed said that we went, right, this one is 407 minus 11, so 396, right? So if we actually measured out our steps, we'd figure out that we were 396 steps from where we started. But because we backtracked by 4 at some point, right, we had to go back over those, so the total distance we traveled was 404, right? So that's all we have this week. So I will see folks next week.